Light travels in a straight line, right? You know that. If I have a light source here and I want to get that light over to that wall, it just goes straight. Why? Why does it go straight and not in some curved way? Well, if you think about it, if it went curved, it would have to travel a longer distance. And since light travels at a fixed speed, a longer distance means longer time. So the fastest way to get from here to there is the straight line. That's obvious. That makes sense. But now here's where it gets interesting. The ancient Greeks discovered something about mirrors. When light bounces off a mirror, there's a rule. The angle of incidence equals the angle of reflection. You've probably heard that. It's one of the oldest laws in physics. The question I want to ask you is, why? Why does light bounce off that way? Why is the angle of incidence equal to the angle of reflection? Well, imagine you're looking at a mirror, and there's a light source somewhere, and your eye is somewhere else. The light goes from the source to the mirror, and then to your eye. Now, there are infinitely many points on that mirror where the light could bounce. Infinitely many. But it doesn't bounce off all those points. It bounces off exactly one point. Why that point and not another? A French mathematician named Pierre de Fermat figured this out around 1650, and he said something remarkable. He said, "The light takes the path that requires the shortest time. Not the shortest distance, the shortest time. So out of all the possible paths that light could take from the source to the mirror to your eye, light chooses the one that gets there fastest." Let me show you why this works for mirrors. Imagine a light source at point B and your eye at point A, and there's a mirror in between. The light has to go from B to some point on the mirror, let's call it M, and then from M to your eye at A. Now, if we think about this geometrically, there's exactly one point M where the angle of incidence equals the angle of reflection, and that point M also happens to be where the total time from B to M to A is the shortest. That's a beautiful fact. The law of reflection emerges naturally from the principle of least time. You see, if the light bounced at some other point M, the total path would be longer, and if the speed of light is constant, a longer path means more time. So nature. And this is the remarkable thing. Light doesn't seem to decide or calculate anything. Light doesn't think, but somehow it takes the path of shortest time. That's what nature does. Now, here's where it really gets interesting. And this is where Fermat was thinking deeply. When light goes from one medium to another, like from air into water, something strange happens. The light bends. It doesn't go straight anymore. It changes direction. The ancient people didn't understand this. The Greek philosopher Ptolemy, around 140 AD, made careful measurements of light going from air into water, and he listed all the angles, but he couldn't find the rule connecting them. It wasn't until much later, in 1621, that a mathematician named Willibord Snell figured out a formula for refraction. We call it Snell's law. But here's the thing. Snell's law is just an observation. It's a pattern. It describes what happens, but it doesn't explain why it happens. And that bothered physicists for a long time. Why do light rays bend at that particular angle when they go from one medium to another? Fermat had an insight. He said, what if light also takes the path of least time when it goes from one medium to another? But wait, light travels at different speeds in different media. In air, light travels at one speed, let's say c. But in water, light travels slower. It travels at about 3/4 of c. So the principle of least time becomes more subtle. It's not just about the shortest distance anymore. You have to account for the fact that light moves at different speeds in different media. Let me give you an analogy. Imagine you're a lifeguard on a beach, and someone is drowning in the water. You're standing on the sand, and the person in trouble is out in the water. Now, you can run faster on the sand than you can swim in the water, right? So if you want to get to the drowning person in the shortest time, you don't run straight toward them. You run along the beach for a bit. Then you jump in the water and swim to them. The optimal path isn't the straight line from you to them. It's a path that spends more distance on the fast medium, sand, and less distance on the slow medium, water. That's exactly what light does. When light goes from air into water, it bends in such a way that it spends more time in the faster medium, air, and takes a shorter path through the slower medium, water. And the angle at which it bends is precisely the angle that minimizes the total travel time. This is Fermat's principle of least time, and it's absolutely remarkable because it unifies the law of straight-line propagation, the law of reflection, and the law of refraction. All three optical laws come from one simple principle. One idea. Now, you might ask, and this is a great question, how does light know which path is the fastest? How does it calculate? Light doesn't have a brain. It doesn't have any intelligence. It doesn't know anything about time or distance. So how does it do this? This question bothered Newton. It bothered Fermat. And it bothered physicists for centuries until we understood the wave nature of light. But I want to tell you about an even more profound way that Feynman, my colleague Richard Feynman, thought about this problem. Feynman said something that really changed my perspective. He said that light actually explores all possible paths. All of them. Not just the shortest time path, but every conceivable path that light could take from the source to the destination. Now, how can that be? How can light go all over the place, and yet we see it taking the shortest time path? The answer involves quantum mechanics and the wave nature of light. But here's the intuition. Imagine light going on many different paths, many different routes. On paths that are far from the path of shortest time, the timing is different. What that means is that when you have light taking one path, the light on a slightly different path has taken slightly different time, which means it has a different phase. When light waves have different phases, they interfere with each other. They cancel out. They don't add up to a bright signal. But on the path of shortest time, and on paths very close to it, the timing is almost the same. The phases are nearly the same. When light waves have the same phase, they reinforce each other. They add up constructively. So the light that reaches your eye, the light that actually has intensity, the light that's bright enough to see, comes almost entirely from the region of paths near the path of shortest time. This is a beautiful explanation. It means that light isn't choosing anything. There's no intent or intelligence involved. Light is just a wave, and it explores all paths. But only the path of shortest time produces constructive interference. Only that path gives you a bright signal. It's a natural consequence of the wave nature of light. Let me tell you another implication of this principle that really shows how powerful it is. It's called the reciprocity principle. If we work out the path of least time for light to go from point A to point B using Fermat's principle, then if we reverse the direction and ask what path light takes going from B to A, it will be exactly the same path. The light goes backward along the same route. This seems obvious maybe, but think about what it means. It means that if you can see someone through a window, they can see you through the same window. It means that the laws of optics are symmetric in time. You can't tell the difference between light going forward in time and light going backward. This is a consequence of the principle of least time. Another beautiful thing that comes from this principle is something that connects different materials. Suppose I measure how much light bends when it goes from air into water. I can measure that and write down a number for it. We call this the refractive index. Then suppose I measure how much light bends going from air into glass. I get a different number. Now, here's the amazing part. If I measure how much light bends going from water into glass, I can predict that number just from knowing the air-to-water index and the air-to-glass index. Why? Because Fermat's principle is so fundamental and so unified. The principle works for any pair of materials. It doesn't matter if you go through air or through something else as a reference point. The principle gives you a consistency relation that has to hold. And when physicists first discovered this consistency relation experimentally, before they understood Fermat's principle, they found it absolutely mysterious. How could nature guarantee this relation? But it all comes from one simple principle. You know, I think one of the deepest insights from Fermat's principle is philosophical. It tells us something about the way nature works. Nature seems to have a preference. Things happen in a certain way because some quantity is minimized or optimized. Light takes the fastest path. In mechanics, moving particles follow trajectories that minimize action. In thermodynamics, systems evolve toward maximum entropy. This principle of minimization and optimization seems to be woven throughout physics. And here's something that amazed physicists when they really thought about it. This principle doesn't require any force pushing light along the path. It's not like light is being shoved along by some mechanism. It's more elegant than that. It's more like nature automatically settles on the path that's optimal. It's almost like nature is lazy. It takes the path that requires the least time. It's the path of least resistance in a very real sense. Now, there's something subtle here that I should mention. Fermat's principle says the path is stationary with respect to time. What does that mean? It means that if you deviate slightly from the true path, the time changes very little. You're at a point where the time doesn't change to first order. Now, this could be a minimum, the shortest time, or it could be a maximum, the longest time, or it could be something in between. But the common case in optics is a minimum, so we usually call it the principle of least time. For example, if you have a concave mirror and light reflects off it, there are actually multiple points where the angle of incidence equals the angle of reflection. Some of these points correspond to minimum time paths, and some to maximum time paths. Light follows all of these paths. The ones that are minima give you the bright reflection you see. The ones that are maxima also physically occur, but they typically aren't as bright. This principle also explains something that seems magical at first: how light refracts through a glass block. Suppose you have a perfectly flat piece of glass with parallel surfaces, and light goes through it at an angle. Light enters the glass, bends toward the normal, travels through the glass, and exits, bending away from the normal. The light emerges parallel to how it entered, but offset, shifted to the side. Now here's the remarkable thing. Even though light is bent while inside the glass, and even though light travels slower in glass than in air, the path that light takes is still the path of minimum time. Light could have taken many other paths through that glass block, but it doesn't. It takes the specific path that minimizes the total time. And because of the geometry, because light moves slower in the glass than in air, light actually minimizes its time in the glass and maximizes its time in the air. This is the beautiful economy of nature. Light doesn't waste time. It balances the fact that it can go fast in air and slow in glass to arrive at the optimal path. This is something that nature seems to prefer again and again. Now, let me address something that people sometimes find confusing. We say light takes the path of least time. But what about when light has to go around an obstacle? What about diffraction? When light encounters an edge or a small opening, it doesn't just go straight. It bends around the obstacle. The light that reaches a point behind the obstacle has somehow gone around it. At first, this seems to violate the principle of least time. If light is taking the fastest path, why does it bend around an obstacle? But remember what I said earlier. Light is a wave, and waves explore all possible paths. When there's an obstacle, many paths are blocked. But the paths that remain, the ones that can go around the obstacle, will still be the ones that give constructive interference. And those will still be the paths of stationary time among all the unblocked paths. The principle of least time is so powerful and so fundamental that it even survives diffraction. It still applies. It's not just a ray optics principle. It's deeper than that. Let me tell you why I think this principle is so important for understanding physics. It's not just that it gives us the right answer about how light behaves. It's that it reveals something about the structure of nature itself. When Fermat wrote down this principle, it was a guess. He had no derivation. He had no deep theoretical reason for it. He just suggested that nature might work this way. And it worked. And then, centuries later, when we developed the theory of waves, we found that Fermat's principle is a consequence of the wave nature of light. The wave nature explains why the principle works. And even later, when we developed quantum mechanics, we found that there's an even deeper principle, the principle of stationary action, from which Fermat's principle follows naturally. This is how physics progresses. Someone makes an inspired guess about how nature works. The guess is simple and elegant. It explains observations and makes predictions. Then later physicists find a deeper theory that explains why that guess was correct. And often they find that the guess was only the tip of an iceberg. There are deeper principles underneath. So the principle of least time is more than just a rule for calculating how light behaves. It's a window into how nature is organized. It's a hint that nature might be described by optimization principles, by the idea that systems tend to extreme values of some quantity. And that idea has proven to be extraordinarily fruitful in physics. You know, when you really understand something like this, you start to see physics differently. You start to see that beneath all the complicated mathematics and all the detailed equations, there are these simple principles that guide nature. The universe seems to prefer elegant solutions. It takes paths of least time. It minimizes action. It maximizes entropy. It's as if nature itself is efficient. It doesn't waste anything. This perspective, this way of thinking about nature, is what attracted me to physics in the first place. And it's what I hope attracts you. It's not about memorizing formulas. It's about understanding the deep principles that make nature work the way it does. When you see these principles, when you really grasp them, physics becomes beautiful. It's not just true, it's elegant. And that's what Fermat's principle is to me. It's beautiful. It's a simple, elegant statement that explains a huge range of optical phenomena. It unifies ideas that seem separate. It tells us something profound about how nature is organized. And it all comes from the simple idea that light takes the fastest path. So the next time you see light reflecting in a mirror or bending as it enters the water, remember this. Nature isn't moving that light according to some complicated list of rules. Nature is solving an optimization problem. It's finding the path of least time. And the fact that it does this accurately, consistently, for every photon, that tells us something fundamental about the structure of reality. That's the real answer to the question, why does light take the fastest path? Because that's how the universe is built. That's the language nature speaks.